fantastic. So, well, Nick covered a lot of my talk already in terms of why you should not use a monolithic system. But anyway, this talk is about distributed systems. How do you deal with microservices and a library that helps you do it? Before we start anything, I would just like to take a small brief of the basic Unix philosophy, because most of what we have done orients around the basics that we have read with Unix. So if we start, Unix promotes this simple rule of composition. You should build short, simple, clear, modular, and extendable code that can easily be maintained and repurposed by developers which are away from just the creators. This philosophy is based on composable as compared with a contextual design. Contextual means that, let's say you have a new business requirement coming in. So you end up changing your previous code. And on the other hand, there's a composable system where let's say you have a payment system. You design the payment system, you have business logic as a separate unit. So you keep reusing the same components that you did once. Wait. It might not work. No, okay. Yeah, cool. Yeah, right. Would this still work? Oh yeah, it works. Thanks. Yeah. So command line tools can communicate with each other using basic pipe operations. So you can take commands, take the output of one command to another command, and you can build a lot of stuff just using your basic tools that would work standalone as well. There's a rule of separation. Separation means that if you have your engine should be separate from the logic. Plain text. You should write programs which only and only communicate via plain text as long as possible. I mean, of course, there are times when you can't use the plain text, and things like a compressor or image format. I mean, obviously if you're transcoding a video or sending a video, that can't happen over plain text. If many of you would have a question here, if it's all plain text, then how does systemd fit in? There you go. That's why people do not like systemd that much. But we can have that word later. Rule of silence. When a program has nothing surprising to say, it doesn't have any information which is not worth it, it should not report it. So tools should be as silent as possible, but if there's an error, it should spit out as much information as possible. Fill your screen, fill your log file, whatever, but only if there's something going wrong. So these are basic 4 things that I would carry to the rest of my talk, because that will explain a lot of how microservices work and should work and why we did something the way it works. Let's talk about microservices. A lot of people over here, I'm assuming that you guys have heard of microservices, and that too far too often in the past few years. It's not something radical that has come up now. It's always been there. That's why I covered it in the first point of Unix. I mean, you make composable units, and you keep using them over and over again. So think of designing software as smaller services. Let's take an example of how traditionally we do it. Like, assume you are a web company, and you would have a front end, then you would have a back end logic, and probably you would have an API and a database. Now, API is where you would fit in all your logic and everything that has to go with the business. Now, we spend a lot of time understanding which language should we choose, which database is perfect for us. The basic rule of microservice here is that you split it all apart. You could be so many people with different requirements in your stack. Like, one guy wants to do it in Ruby, the other guy wants to do it in Java, the other guy wants to do it in Go or any other language. have smaller services which can talk to each other as long as they run as their separate processes. They talk to each other using a very lightweight protocol. It doesn't have to be HTTP as well at times. And they have a common exchange mechanism which is readable and debuggable at all points of time. This is the whole basis of having a microservice architecture. Now, what are the drawbacks of using a monolithic architecture? Actually, the last one should be the first one. You always know who to blame. Like most of the time, there's a bug that crops up in your system. You spend days and nights understanding who this bug belongs to. Microservice architecture will actually help you do that. So they'll help you understand who is the guy who's responsible for this bug. Anyway, so the division of organization and responsibility. You don't divide your code as per the speciality of a team. So you don't say that this is a UI team, this is a backend team, this is a database team. You divide your code as per the component. So a payment system could have all the three people in it, as long as they adhere to a common principle and a common functionality. They should all live together. Now, in a traditional system of a monolithic system, you could have a single update which has to go out, but for the same reason, you'll have to reshape your entire application. Now, compared to the microservice architecture, the service could be deployed. It could restart as many times as you wanted, only basis of that particular service. Also, let's say if there's a common function. Let's say if you are a messaging company and there's a message that comes in. The video has to be encoded or transcoded. Now, this is one particular function that will consume a lot of your CPU. It could bring down your entire application as well. Stuff like this, you start offloading to microservice. You make a separate service, which is only and only responsible for encoding this video for you. Now, if your application has to scale up, you know that this is the exact point of failure that usually fails for you. You deploy a whole cluster of such things. Have 10, 15, 20 odd, whatever you want. But the rest of the application runs in the same way. So coming back to this, the only difference is like how you design libraries in a code. Like you use a shared library. Think of it microservices as the same way. It's just that it's a separate process running this time around. It's the same concept of a shared library. Just that you run it as a completely delegated separate process, which is easier to monitor and scale as well. Now, this talk is about this library that we have built, which is called Gilmour. Gilmour is it is a small DSL. It started off as a small DSL. Now it's a full-blown library in itself because as it has grown, it has come of age. This was started as a small communication protocol which would allow developers in a team to exchange messages and build smaller microservices which were not using HTTP. Now, it's simply, it's actually, how many of you have used Sinatra here or heard of Sinatra? Yeah, think of the ability to do Sinatra, have routes and have logic there, just that this is not HTTP. It works on PubSub backend, which is, we use Redis for it. It started off with using AQMP as well, but that support had to be dropped down eventually. So, yeah, so through this talk, we'll actually go through how you can use Gilmour to design such libraries and such systems for you. Let's also start understanding what are the basic high-level architecture patterns for a distributed system. Now, distributed systems are all of you, I'm assuming, are aware of what design patterns are, right? So design patterns are basically just a way of identifying common problems and having a few terminologies which help you represent that problem so that you can communicate easily and in a more effective manner. Like one of the basic patterns of a distributed system is an observer pattern. Is this visible or should I zoom in a little? Better now? Yeah. So assume there's a publisher which is publishing messages. And there is a pub sub receiver at the bottom, and there are a lot of subscribers to it. So you see subscriber A, subscriber B, subscriber C, subscriber D. Now, the observer pattern, it's probably been around since 1994. It's so popular that people in Java and C# have named inbuilts around it, like the observer and the events. Has anyone ever worked with Qt here, the KDE library? So, okay. So, one common way of implementing an observer pattern is signals and slots. So, what you do is you send out messages and you have a receiver on the other end. Now, the one who's sending out the message may or may not know about the receivers. There could be more than one, there could be none. The sender doesn't care. People have worked with spreadsheets. Let me give you a very basic example. I'm assuming everyone has worked with spreadsheets here, right? Now, in spreadsheets, you write formulas. You have a cell where you apply values. Then there's another cell where you would do certain sort of formula. And every time you change the values reflect in that destination cell. Now, how does this work? This works pretty much this is exactly what observer pattern is. So the destination cell is bound to an event. The event is emitted every time you change a certain value in the cells, which lead to the value change. Now, if you play games, you unlock achievements, etc. Right? How many of you play video games here, or regular games on your cell phones all the time? Right? I mean, a common example is you fall off a bridge, and the game unlocks an achievement for you, which is gravity defied. Now, these achievements could change over time. It's not hard coded into the core code. So this also uses the same pattern. So there are events which are emitted at all points of time. So it would be as simple as that the moment the physics engine detects that you have fallen off a bridge, it emits an event, fallen off the bridge. Now, whatever the achievement is or whatever it has to happen corresponding to it are your slots or receivers. Now, there could be one, there could be many. You could have one achievement of being too foolish in the game. Another slot would be end the game because now you can't move ahead in the game. There could be another accomplishment. So you can have these things, and this is the ground of designing a scalable system. Like, you can get the idea of how this system would become. So the core code is only responsible for sending events. On the outside, you have a separate service, or you could have many services which are responsible for trapping those events. Push notifications is also one example. I'm assuming everyone uses WhatsApp here, right? Now, when you send a message, your application doesn't block until that message is sent out to every one of your friends. Now, that is the same pattern that you would follow here. So this diagram, and one of the most common exchange formats of such things is topics, topic exchange. So a publisher says that I'm going to send messages to this topic. The receiver also adheres to that topic. And then you have a central broker, which is PubSub in this diagram. That is responsible for ensuring that the message is delivered to every receiver who has subscribed to that topic. There are actually a few drawbacks that might come into your head when you think of observer patterns. One is memory leak. So it is possible that you keep sending all these messages, but there's no receiver at the end of it. So your memory could bloat up. It's very well possible. There's also a huge headache which is involved here of having to clean up messages after they are consumed. There's also no guarantee of a return. Like, sometimes you send a message, but you don't know whether it's going to be received or not. It's much like UDP. Like, you send a message, but you don't know what's going to happen to it. So fair to say that 60% of the time, the message would be delivered every time. Just to say. Now, Gilmour will actually help you overcome all this because Gilmour doesn't use a persistent queue. Messages are not stored anywhere. Messages are sent, they are consumed if there's a receiver, and destroyed thereafter. So this problem of memory leak, etc., is not supposed to happen here. That's one advantage I say that we have over rest of the systems. Observer pattern have a few characteristics. Signals and slots I've already covered. Broadcast, fan out. It's a common practice. So you have a message which is being sent out, but you want to send it to as many people, as many receivers as you want. As I said, there could be multiple receivers. This whole policy is called fanning out. There's another very crucial component which is peculiar to observer pattern, and that is wildcard. A subscriber can say, hey, I want to subscribe to everything which is hello.star. So if a message is being sent to hello.world or hello.foo, hello.bar, that subscriber would receive all these messages. Responses are disabled. There's no concept of a response delivery. There's no response channel because once a message is sent, the emitter doesn't care about it anymore. Also, the receivers are responsible for their own failures. Because there's no communication back and forth, if there's a failure that happens in a receiver, the receiver is supposed to take care of it. Let's look at this example here on how using Gilmour you could come up with a small thing. So this is a server class that we have. Then Gilmour is a backend that is using Redis. So we instantiate a backend, Gilmour. Waiter is just a small wait group. It's just a small mutex that takes care if the program doesn't exist. The first thing that we do is we add a slot, Gilmour.slot. It subscribes to a topic, which is user.added, and it does a certain routine in the middle of it. There's another one. I think I added the same code again. Yeah. So in the last line, you see, every time you encounter EM in the Gilmour code, it's basis of event machine. I'll cover that part later. I think I skipped that. Yeah. So Gilmour.signal sends out a signal with a data format, which says, such is the hash that will be submitted to user.added topic. Now, whosoever is responsible for user.added takes care of it. So over here, we have two slots, user.added. The first one and the second one. Both of them would be executed because they can have as many slots as possible. The other counterpart to the observer pattern is a request response pattern. Request response pattern is another design pattern which is followed in distributed systems. All the shortcomings that we discussed about the observer pattern are taken care of in the request response pattern. The problem of no return is handled because so it's more like, so assume that we are making a communication, right? You know walkie-talkies, where you send in a message, you don't know who's going to receive it or not. That's more like the observer pattern. The other pattern is like a regular telephone call. You know the person who you're calling, the person responds on the other hand, and that's a request response pattern. Let's take that in detail. So you'll have to do with this because it's horizontal, I can't zoom in further. So the request response pattern would go like, there's a publisher which sends a message, hello. Hello is sent to the broker. Brokers relays it further to whosoever was responsible for it. Now, at this point, there's also a relay chain which connects back and sends the data, which is the response. Now, this response is very crucial here because this is primarily what differentiates a request response pattern for an observer pattern. Think of regular client-server architectures that we have, like HTTP. You send in a request to a server, the server sends you a response in a finite amount of time. That is a request response pattern. It's blocking, but it can be thought of the same thing. Most of the times, it is assumed to be synchronous, that you send in a message and you get the response. The sender is blocked on a response, or you could do some sort of I/O multiplexing and you could wait for the return to come, but still you're waiting for something to happen. Now, there are few characteristics of request response pattern, which is also called request reply pattern. There are few characters, at least once delivery. Now, since we are saying that there is a response being generated, a message must be delivered at least once to at least one of the subscribers. Timeouts. Timeouts is one of the most crucial parts because you can't keep on waiting for the response to come, especially in a distributed system where there could be delays or failures. It's essential that there's a finite cap to every job that has to happen. Timeouts can happen on the emitter side. Timeouts can also happen on the subscriber side. Like a subscriber is only allowed to work for, say, 10 minutes. The receiver is only going to wait 20 minutes. So such timeouts are always have to be there. Response or error has to be guaranteed. The server either returns with a valid data or it shall return with an error, but there will be something. It won't be the case where it doesn't return with anything. Mutual exclusion. This is probably one of the interesting most parts of request response patterns. So the same set of subscribers, if we go back in this slide here, right? Now, think of it like subscriber A, subscriber B, subscriber C, and subscriber D are all separated in multiple regions of yours. So you have a single application, but these are receivers deployed across your regions and cluster, different of them. Now, but you only want that only one guy should process this message at a time. So you add them to mutually exclusive groups. So you say that subscriber A and subscriber B are a part of a mutually exclusive group. What that guarantees is that only one of these members from a certain group would receive the message. That way you ensure that there is no duplication or no to, assume you're coming up with a payment system around such a pub-sub distributed architecture, right? You don't want a same payment to go out twice. Does that mean thrice 5 minutes? Seriously? Oh, okay. Yeah, so we take the same example here, this one. Now, this is a small Fibonacci series generator. Now, the same thing, same server created, same backend created. In a handler, what we do is we take our first values and we say Gilmour.request. Now, there's a first value coming in and there's a second value which goes in. There's a timeout of 5 seconds, so no job is going to run for more than 5 seconds. Then after we get the response, you look at the last line. It calls the handler again. So the handler calling is a thing which is happening recursively. There's a reply to pattern which listens on a particular topic. It has an exclusive group which says Fibonacci, and there's a timeout. So the subscriber is going to take this message, is going to add it to a response, and this cycle keeps going on. Now, this is as simple as what it would take to design your application around this. Common expectation. Irrespective of which design pattern you follow, there are few expectations that both the systems have. First is asynchronous messaging. Now, one thing that I should also add here is, how do we handle this in Gilmour? The whole part of request and response. So every time you send in a request, Gilmour actually takes that request identifier, registers for a separate topic, which is response that particular sender. So it is synchronous over asynchronous. So nothing is being blocked. It's just that when the subscriber is done with processing the result, it publishes a message to the topic which was previously subscribed by the sender. Did I explain it clearly? So what that means is that you don't block your application, and when the response occurs, the response is being sent to the caller. Yeah, coming back to common expectations, Low latency. When you're designing distributed systems, you expect it to be absolutely fast as possible. The fact that we don't use any HTTP communication, we only use Redis protocol, I mean, it's definitely significantly faster than that. Concurrency. Concurrency, every time we speak of concurrency in distributed systems, we mean three sorts: logical, physical, or distributed. Logical concurrency means that you're actually separating out your code logic. They could be running parallelly next to each other without bothering any one of those. Physical concurrency, you could have your Gilmour listeners across the region, as we demonstrated. You don't care where it is running. Or it could be on a same machine. It could be on a same machine where each request is being served in a different fork or a process. That's physical concurrency. And distributed concurrency is also taken care of. Per message UID. Every message that you send out must have an identifier associated with it, because when you're looking at a distributed log, the timing and the order is irrelevant. It's something which is not even guaranteed. So for you to be able to associate in the logs on what is related to each request, a request ID is mandatory. Failures. If it's a distributed system, assume it's going to fail. Things fail all the time. Like if I was to say this to a normal guy that something failing, the probability is 10 raised to power 13, people would say that's too rare. But if there's a physicist here, he would say that that would happen all the time. So, and that's also true for networks. Things just fail, like if they have to. There are few common fallacies of network design. Networks are always unreliable. Latency is always infinite. Bandwidth will always be limited. Networks are heterogeneous. And with Gilmour, we actually try to address all of these. The fact that we have timeouts ensures that there are no long-run jobs. So the latency part is taken care of. Fault diagnosis. Every time something fails, you must be able to do something with the error logs that you have. Gilmour allows you a way to broadcast your errors. 1 minute left? Is it really, is your clock working fine? No. Oh, okay. So, all right. So I'll try to be as fast as possible. Yeah. Does my laptop fixing time eat from my speaking time? No. Anyway. So error broadcasting, error queuing. So you could queue all your errors, or you could just ignore all your errors. Service composition. Coming back to the Unix philosophy, this is probably one of the most unique and best features of Gilmour. You can have commands. So think of every job as a command. So you can have commands which could run in parallel to each other. So you could take output from one, pass it to the other one, pass it to the third one. This is called simple composition. And. People who use Linux would be fairly comfortable with this one. Do command 2 only if the command 1 has succeeded. Now, Gilmour allows you a way to construct such commands as well. Batch jobs, you could run all of them in parallel. You could do twists and turns around it. You could capture the output in a group. All of this is possible using Gilmour. Combinations, you could take any of the previous previous continuations that we discussed, and you could make any combination of it. So you could have a batch, you could have an and, or you could have a composition, and you could think of it like Lego. You can just make anything with it that you want to. Continuation. Every Gilmour request, if it's a part of the composition pattern, it will also give you a continuation. So if you have a request which had 5 things to be done, and the request fails at the 3rd command, you can still have the continuation and perform those commands later, the rest 4th and the 5th one. I could give you a small, quick Yeah, can you see this code? Is this readable? Yeah, so these are just a few topics that we have subscribed to, 1, 2, bad 2, 3. And here we are creating a composition. This composition is basically send in message 1 topic, then send it to topic 2, and then send to topic 3. Now, this part takes your message and actually carries it over. So each one of the listeners are going to take care of it. This is the composition part. Then you can have an and as well. It's pretty easy to construct. When you execute, you can pass in a block next to it. This block will have data or code, or it can have a continuation. This continuation is important because let's say 1, 2, 3, 4, 5, 3 failed. You can have the 4th and the 5th one that you can execute separately. Can I have just 2 more minutes? All right, thanks. Message exchange protocol. Now, since we all agreed on the part that it's best to communicate with plain text as much as possible, we use a consistent data structure for all the request responses. So there's data, there's sender, there's code. It's a simple JSON, human readable, you can read it. The errors also follow a homogeneous pattern. All errors come in this format. All errors are supposed to have the same sender ID that you can associate in the logs as well. And it's human readable because I'm assuming that humans are going to debug it at the end of it. Quickly coming on to the language support part. Wait. Why did it not work? Yeah. So Gilmour has been implemented across many languages, which is, it started off with Ruby, but there's also support available in Golang and Java. So we adhere with the same principle of microservices, so you can actually choose to write your services across any languages that you want. Then comes the part of failure handling. Since it's a distributed system that we're talking about, things could fail all the time. We advise you that you have a look at this library called Hystrix by Netflix, which takes care of secondaries, failovers, back pressure management, and circuit breaking in case there's a failure. I think we're done. All right, cool. So this is pretty much, we're out of time. You can check it on GitHub. The source code is there. There are a handful of examples. And if you have any doubts, me and the Gilmour author, who is also present around here, you can catch us and you can have your questions. That's it.